Okay, guys, so we're back for maybe one last example on how to pair up an infrared spectroscopy signal from a mass spectroscopy signal. And we're going to use those two to identify a molecule. And not only are we going to identify the condensed structure, but we're going to go through and actually give you how those atoms are hooked up. So here's another example. And up at the top, I see the infrared, and then down at the bottom, I see the mass spec. Now, I am given the task to figure out how this compound is actually going to connect together and what the compound actually is based on a couple of squiggly lines. All right, so the first thing that I want to do is maybe take a look up here at the very top. In the infrared, the very first thing that I'm noticing is this big, strong signal that's going to be right here. This is at 1700. And we said that anything at 1700 is going to be a very good sign that we have a C double bond O. Again, you thought those had disappeared from the last test, but you were wrong. All right, so under the C double bond O, I've got a couple of options. Number one, is it a carboxylic acid? And the answer is no. I don't really see a big dip with a jagged little end that goes back up. Do I see an aldehyde? Well, that's at 27 and 2800. So 27 and 2800 is going to be about right here and right here. And if I go up, no, I don't see a double peak. All right, well, what other kind of types of carbonyls do we have an anhydride? Well, no, that would show two of them at 1700 and 1800 or 1600 maybe. Only see one. So in the area of 1050 to 1300, I see clearly one major peak. And we've said before in the past that if we had that combination, I told you that we would label it as a ester / ketone. The problem, though, is that this is very clear cut, so it really isn't even a problem. There is one major peak that's there, nothing else. For that reason, I'm going to go ahead and make the determination that this sucker is a ketone functional group, which means that there is a carbon on each side. All right, so I at least can use this as a building block to figure out what type of compound that I have. Over here in the mass spectra, it looks like the base peak that's here. There's 40, 41, 42, and 43. And then here at the M peak, there's 80, there's 85, and it looks like it could be 86. Notice that little bitty squiggle right there. That probably is due to an isotope. And then if you look really closely, you might confuse yourself. Maybe not confuse. But it looks like there's going to be a small little peak right there. Now, is that something just on the line? Is that something that's appearing? Is that the actual M peak? Well, we'll get to that point when we cross it. But I'm going to use 86 to begin with. All right, so we know that we have a carbon, double bond O, carbon, and carbon, at least. The object of the game here is to get an 86, possibly for my formula weight. So I'm going to bring up the calculator, and I'm going to add these up the way that I've drawn them already. 12, 12, 12, and 16. That gives me a 52. Well, let's just add another carbon on. If we add another carbon, that's another 12. That gives me 64. Now, if all of these at this point in time had the proper number of hydrogens, there would be 3 here, 2 of them there, 3 of them there. So 3 and 3 is 6 plus 2 more, that's 8. If I add on 8, it doesn't get me to the 86. All right, so I'm going to subtract those 8 off. I know there's still more to go. So I'm just going to kind of make this symmetrical in the beginning. That's typically what I do. It might not be right, but it's typically what I do. All right, so there's another carbon. That means I'm going to add another 12 onto this molecule, and now I get 76. Well, I'm getting really close now, right? So there's 3, 4, 5, 6, 7, 8, 9, 10. There's 10 hydrogens if I stopped here, and that would bring my total to an 86. Now I'm going to go back to this mass spec. Remember I said, well, there looks something funny down here at 100. It looks like a little signal. Yeah, it does look like there's something there, but you know what? This is a ketone. If this was an OH group, an alcohol, we said that alcohol molecular peaks really don't go through at all. They're not going to be very major. But it's not an alcohol. We know that from the infrared. All of the other M peaks are pretty dominant, meaning that you'll be able to see them if they're present. Just like the 86 that's here, this thing is fairly large, right? Your eyes go to it, you know that it's an important peak, and we've labeled it. The only one that you really have to question that way are the alcohol functional groups, because they can be super, super tiny, because most of the time the entire fragment does not go through. Just with the missing electron. The OH is going to pop off of there when it can. Now, this is not the only way that I can draw this structure. It does have an isomer, right? So I made the choice. Now, this is how we started out, and we have to start out this way. And I said, hey, listen, we're going to add a 4th carbon on. And that's what we did to this side. And then I said, well, we're going to keep it symmetrical. Now we're going to add that 5th carbon to the left. And this gives us a nice, pretty, even molecule. Well, I didn't have to do it that way. I could have just continued to chain out in this particular manner. Well, that still adds up to 86, right? CH3, and then we have a CH2, and then we have a CH2, and then we have a CH3. No big deal. I've got 2 choices. So the question is, can I determine which one of these this combo is going to represent, right? So I'm getting closer. Based on the infrared, based on the MS, I can at least tell you that this is a 5-carbon ketone. If I had to go up here and name them, just a review of organic chemistry. If you're not in there yet, don't worry about it. I'm not going to ask you to do this on the mass spec test. It's really organic, not instrumentation. Well, this is a ketone. 1, 2, 3, 4, and 5. So this is a pentane. Erase the E, add O-N-E for pentanone. And this is at carbon 1, carbon 2, and carbon 3. So this would be called 3-pentanone. And over here to the right, 1, 2, 3, 4, 5, longest chain. That's a pentane. Drop the E, add O-N-E. To tell me it's a ketone, and then at carbon number 2 I get the carbonyl functional group. Now I've got to figure out, is there a way that these molecules will fragment in such a manner that will give me something that closely matches to this infrared down here at the very bottom? So if we go back and take a look at how ketones will kind of break apart, we've already discussed this concept that they do it at the alpha carbon, but you know, they also have a special kind of way that they will fragment at the same time, and this is through the McLafferty rearrangement. So I've got to keep both of these in mind. Now, remember, McLafferty rearrangement does not happen unless you have a gamma carbon on the structure. Otherwise, you're not going to see McLafferty. So this is something that I can't forget. And we also have a alpha carbon cleavage that can happen as well. All right, so here I'm going to go back. There's the infrared and there's the mass spec all over again. And I'm going to go through and just start chopping these things up. All right, so I told you that this is typically what we would normally call an alpha carbon with the alpha carbon cleavage, and I'm going to chop it off on one side. When I do that, these electrons, they can go away, move in to the C double bond O and create a positive charge that's going to be there. So I need to go through and I need to probably add up that type of fragment. So C triple bond O, that carries my positive charge, and then my CH2, and then my CH3. However, that's not the only side, excuse me, that this can happen on. So I'm going to erase this choice that I've just did, and I'm going to chop it on the other side. Well, if I do that, I'm left off with the same group that I have already, right? The electrons move in, a triple bond gets formed, a positive charge tags onto the molecule, and I get this C triple bond O with 2 more carbons. That's exactly what I've written down here at the bottom. So I'm just going to put ×2 here just to let me know, yes, I did check that choice, and yes, it's going to show up again statistically wise. It's got 2 options that it can use to form that fragment. All right, so I'm going to go back to the original structure. And now we need to talk about the proper alpha carbon. Remember, we said that the carbonyl group is part of the functional group. So that really isn't the alpha carbon. This would really be the alpha carbon. So there's alpha and there's beta. And then on this side, there's alpha and there's beta. So as far as McLafferty goes, there is no choice for McLafferty rearrangement here. I need that gamma carbon in order to break this ketone down the way that it should be. And I don't really have it. So I'm not going to see another fragment based on the different weird ways that a ketone could break down. Now over on the other side, we'll do weights of these in just a second. Over on the other side, we'll do the same thing. This molecule can cleave to the left, and what we would have is a C triple bond O with a positive group with a CH2, a CH2, and a CH3. So there's one type of fragment that I could get. All right, so I'm going to erase that option. We've already done that. And the second option that I have with normal cleavage is going to be here to the right. So what I would have in this case would be a C triple bond O with a positive fragment, and then the CH3 to the left. That is a different fragment. That positive is on a different piece of the molecule. So this is going to give rise to a second fragment. All right, now let's check the strange, weird way that McLafferty could probably come into the picture. So again, this carbonyl bond is really part of the functional group, so I can't really count that carbon. So this is the true alpha carbon right there, and this is a beta, and this is a gamma. So the question, yes, McLafferty rearrangement can happen. So the way that this works is that this C double bond O will actually go, and remember, it will pull off a hydrogen from that particular carbon. So a hydrogen is going to be slapped onto that oxygen, which is what gives it that positive charge. In the meantime, it's going to take one of the electrons and it's going to shove them in here and create this 2-carbon alkene, and then this molecule gets chopped off at that location, and away this goes. Okay, so what we have left over is our CH2 group, and then over here is our CH3 group. All right, so here's my positive fragment. That is a McLafferty rearrangement, and that's what we saw in the PowerPoint slide just a second ago. And again, here is a review if you need it. So there's the gamma carbon. Let me go ahead and erase this mess, just so we can clear that up a little bit. There we go. All right, so alpha, beta, gamma. We do have a gamma carbon in our case that we're working on now. This hydrogen gets pulled off and it slaps onto that oxygen to create this OH group that's positive up here at the top. One of these electrons go inward, one of these electrons go inward, creates a double bond, and those two go away, and that's what we're seeing over here. And then what we're left over with is basically this remaining fragment, just with a H on the oxygen instead. All right, so it is kind of like an alpha cleavage. It is truly cleaving at the alpha carbon. Away it goes. And then we're left over with a remaining fragment that has a hydrogen on it. So we get a +1 from that fragment. All right, so now I'm going to go through and I'm going to do a fragment weight of each one of these guys. All right, so we're going to start with the first one to the left. That's going to be a 16 and a 12 and a 2, a 12 and a 3. And we're going to end up getting a 57. So 57 is going to go here. And there's no really other fragments that are kind of common that we would just associate with a ketone. Now keep in mind, this molecule can break up in a number of different pieces. I'm not saying that that CH3 group at the end cannot come off. It can. But according to the rules that we've talked about, they have a tendency to do certain fragments. We are doing the tendency of those fragments. We're not listing every single thing that can happen. We're just listing some of the major things that will go on. But that molecule can fragment in more than just the 57. But if I'm looking at it, and if it has a preference, then that's what it's going to show me. Over to the right-hand side, the same thing's going to happen. This molecule is going to break up in a number of different ways. I'm not listing all of them. I'm just listing kind of the top runners of what could happen if it does break up. So these are kind of like the priority ones. So I'm going to start with the top one. That's a 12 and 16, a 12 and 2, a 12 and 2, a 12 and a 3. And this gives me a 71. All right, so a 71 is going to happen there. I'm now going to do the second fragment option that we did. So that's a 12 and a 3, a 12 and a 16, and that gives me a 43. And then I'm going to do the third option, and that third option came from the McLafferty rearrangement. So 12 and 3, a 12, a 16 and a 1, a 12 and a 2, and that gives me a 58. If I take a look at both of those up at the top, keep in mind that formula weight is going to be an 86. So both of those would show an 86 for me. All right, now if I go back to the mass spec, what I'm seeing is that there is a huge base peak. That means this is a preferred fragment that this molecule will break into. And that preferred fragment is a 43. So I'm going to go back to my two choices, and what I would see is that there was only one way that I could get the 43. The one to the left doesn't quite give me 43 commonly. It gives me 57, and it does give me some of the other fragments that we've not written down, but that's kind of the major one that would happen, would be that 57. That's the preferred way it would break. Well, over to the right-hand side, one of the preferred ways that this molecule will break is to give me a 43. And that just so happens to match the base peak of the mass spectrum. In addition to that, what I would also see is a 71. And right here is the 71. On top of that, we've also written down a 58. I'm going to go to the spectrum. There's 55, 56, 57, and 58. So I have identified that peak. I've identified that peak. I've identified this one because that's the molecular weight. I've identified this one, which is 43. A lot of those fragments match to the second choice that I've written down on the notepad. So that's going to lead me to believe that out of these two options, I can probably identify pretty comfortably that this molecule is 2-pentanone. So my carbonyl is on the second carbon, my carbonyl is not on the third carbon. So this structure does not break down commonly in a way that will match this mass spectrum that I'm seeing here on the screen. Now, with that said, we also want to talk about all of these others, right? Because we did not label those. Well, I keep mentioning over and over and over, these are just the most common fragments that I would see. I'm not saying that the molecule cannot break up in different ways. I'm not saying that this molecule can't just give off a CH3 group or a CH2CH3 group. It can, because think about it. We said that if the molecule cleaves this way, then that gets the positive charge. Well, what I'm left with is a CH3 after this point, right? Well, nothing says that the positive can't go to that CH3 sometimes. We've already discussed that possibility in that scenario. Well, right here is going to be my 15. That's going to be a CH3 group, a 12 with 3 more carbons. So that's where these other ones are coming from. Again, we're not saying that they can't happen. What we're saying is that these are the major ones. These are what I would see most of the time. These should be somewhat of the major lines that appear on the mass spectrum. And if I can get these numbers to match, or a lot of them, then this is a very good indicator that this compound is represented in that mass spectrum. The one to the left only gave me a 57. That was the major peak, right? And if I go back to this infrared and I go to 57, there's 55, 56, and 57. It's going to be right here. I'm not seeing a major peak at all there. I see one at 58, but not at 57. And because of that, it probably means that this molecule does not match that mass spectrum. So once again, we have used an infrared and we have used a mass spectrum to completely identify a molecule that was injected. And I wasn't there to inject it. I had no clue what got shot onto those instruments. And based on a series of squiggly lines from 2 different instruments, I was able to determine the complete identity, including isomers, the complete identity of that molecule that was analyzed. All right? So you're going to see quite a few of these types of questions that appear on a test. And I need you to feel comfortable with this. I need you to go through and maybe try these all over again. And I need you to work out some examples. I need you to go back and take a look at infrared. Make sure that you don't get kind of weirded out on the functional groups. Make sure that you know them, because the interpretation of the infrared up here at the very top is going to be a key part to the puzzle, because that's going to tell us the functional group that we need, which will give us a starting formula weight. And from that piece, we can build off of that. But without that piece, if I identify that wrong, then I'm just fighting a losing battle. I'm not going to be able to figure out the proper way that this molecule needs to be put together in order to give us this infrared and this mass spectrum. All right? So review your infrared. Make sure you feel comfortable with those. And then use that as the starting or the building block to build everything else up on. So good luck. I think this is where the mass spectra lecture is going to stop. I know it was a long one, but I told you it was going to be that way before we even started. So there's a lot here. A lot to the equipment, a lot to the theory, and a lot to the interpretation of what the data means. So good luck. Let me know if you've got any questions.